So, yes. Guess I'd look at some other things here. So, well, can roll into this slowly on a cool Wednesday morning. I guess our penultimate class, right, together? Or ultimate class in some cases. So talk a bit more about open channel flows again. We talked about uniform flows, which would be the ditch like you see along College Avenue that's by Alexander dealership when it's been raining in State College, just flows as a stream, constant head, shallow gradient, no change in, although you can't tell, no change in depth as you go downstream. And we talked about gradually varying flows and rapidly varying flows. And I guess this is probably a rapidly varying flow where you change from being shallow and fast upstream, the kind of silvery water or smooth water, and then downstream, which is the pillow, which is deeper and slower moving and also turning back on you as well. And so we'll finish off a little bit on uniform flows today, which we talked about on Monday, and talk about gradually varying flows and then rapidly varying flows on Friday. So, of course, there are many examples of these. Always dangerous to, well, I guess we also showed a hydraulic jump last time as well. Which I guess is a view of what we just saw, but a section through it. Upstream, fast and shallow. Downstream, slow and deep. Continuity, you can apply velocity times cross-sectional area, which for a flume, which is just an aquarium of constant width, it scales with the height. So velocity times depth here and velocity times depth here have to equal each other. And so I guess that was the essence of one of the homework examples. And that was your question, right? Why doesn't Bernoulli work out? Yeah, so we'll talk about that on Friday. And what else? It was dangerous to do this. Never know what you might find. Yeah, that's it. This is a stream coming out of the Alps. The Alps, like some of the Rockies, are limestone mountains, a basin that was then compressed on a subduction zone and now has big water flows which are characteristic of karst and limestone, like actually is under our feet in Pennsylvania. And this is just one stream that's coming out from a spring in there, big volume spring. But you see upstream, it's nice and smooth. It goes over the brink. You can actually see the little dam underneath it because it's so clear in the water that the water's so smooth as it goes over the top. And then downstream, it breaks up into a pillow just as before. So it becomes a smooth flow, then becomes, I guess, a rapidly varying flow downstream. And I don't know whether there are, actually I think that is. I was going to say I don't know whether there are slalom wires there, but I think that's exactly what that is, to hang slalom gates for whitewater kayaking. So quite amazing to look at. So, and so that's what we're talking about, the fact that we have this extra degree of freedom going on. So this is actually on a site visit to a former ballistic missile silo in France, of all things, which is now cleared of all those missiles and used as an underground research lab for looking at reactivating faults and looking at induced earthquakes and things. So that's the particular reason for that. So that's a bit of background of what we were talking about. All right, let's get rolling with this. We didn't quite finish off last time, right? So we were talking about uniform flows, and we were talking about the Manning formula, Shesi formula, Manning formula. where the depth doesn't change as you go downstream. We've cut it short because we kind of ran out of time. But the bottom line was, and all that you would need to know, is that we can define a volumetric flow rate or an average velocity coming out of a stream flow as a function of the slope of the bed. So the slope of the bed, if you recall, was just the length times the height. This would be the water on top of it, flowing downstream at some velocity v. And so S0 is just the gradient, the change in elevation divided by the length over which it occurs. And so gravity is driving the flow. And so this is the motive power, which is really, if you look at the energy equation, this would be the pump head. This is the hydraulic radius. Hydraulic radius is equal to the area over the perimeter. And Manning's coefficient, we rationalize the fact that it's a single value because we're always in the regime, which if we look at Moody charts, we're always in this right-hand regime. So you can define a constant, which is a small number if it's smooth, which is a bigger number if it's rough channel, and those numbers exist, which we'll look at in a second. And so it's just formulaic. This coefficient depends on whether you're in SI units or English, and the units matter in this particular equation. Meters and seconds for this, if you're in English, or feet per second if you're in imperial or English units. Volumetric flow rate is just the average velocity times the cross-sectional area of flow. And I guess we drew this in perspective so that this was, in terms of all our components, this is the length, this is the area, the perimeter is just this plus this plus this. And so easy to get this. And the slope would just be delta z, which would also be the slope of the surface as well, right? Because we said that the water slopes at the same amount. So this is just delta z, and this is also delta z. And so if you have a section that you want to use, you can divide it into different parts depending on if you have a Manning coefficient, which I suppose we should talk about, depending on whether it's, they should be smaller for the smoother ones. So a glass channel, not many of those exist, I guess, but steel, if you have cast iron, or if you have a culvert, which is those corrugated steel ones, this is larger than a smooth one. So Manning's number increases as you get progressively rougher. So these are progressively rougher going down here. So this would be increasing epsilon over hydraulic radius, I guess, right? This would be increasing values of this as you go down here. Likewise for these. So you need to choose one that's equivalent for your, appropriate for your system. You can use compound channels by having different Manning numbers. Perhaps on a floodplain you might be flowing through weeds, and this might be a real channel which is smoother. So this would be, I guess it's the opposite here, isn't it? This is larger in the middle than this. So perhaps it would be the other way around. Flowing through weeds here and flowing through a channel here, then you'd expect this Manning number to be smaller because it's smoother. If you have a very wide channel and you define the hydraulic radius as the area, which is the width times the depth, and the perimeter would be the depth plus the width plus the depth, so b plus 2y. In the limit, if b is very wide, then this goes to just being the width. The b's drop out on top and bottom. And so this ends up being an approximation. If you have a compound channel, you can divide it up into a number of segments. Each of these segments must have the same volumetric flow going down it. So there'd be Q1 going down into the page. There'd be Q2 going down here and Q3. So you can just sum up those individual components and you'd get the magnitudes from this, where this is the cross-sectional area of each bin and this is the hydraulic radius of each bin. And I guess the only thing to remember is that the areas of these would be the areas you see, but because you're dividing it up within the flow velocity on this side of the dashed line and this side of the dashed line is the same. So there's no drag on that boundary. And so the perimeter you use would only be for A1, it would be P1. It wouldn't include this part here. The perimeter for P2 would be this. It wouldn't include this or this. And the perimeter for P3 would be this, as opposed to the areas are just the areas. And so the hydraulic radius for these would be, so this would go to being, hydraulic radius 1 would just be equal to A1 over P1, where it's, obviously just the wetted perimeter. So this is the wetted perimeter. And finally, I guess, there are sections that are the most efficient, that would carry the flow. And you could do that by maximizing the flow for any section. They're just standard results. And the maximum flow section would be a rectangle where the depth is half the width. A triangle, which is a right angle triangle on its edge. A section of a circle which is filled to half, or a semicircle which is filled to full, or a hexagon which has 60-degree sides and is the same lengths on each of the sides. Just standard results that come out. So that is that. And there's an example in here. Pretty easy to go through. Again, you just need to work out the dimensions for this, so you know that the expression you need to use is this for flow rate, this, I guess. So this is in English units, so instead of being 1, it's 1.49. A Manning coefficient, which you need for this particular lined, which is smooth concrete, so you know that. Cross-sectional area, and a hydraulic radius to the power 2 over 3, and the slope of the channel. Slope is dimensionless. It's equal to 1.4 over 1,000, delta Z over the length of flow. The hydraulic radius is equal to the area of the perimeter. I guess for this you'd need to do some hijinks. I think you bottom drops determine flow rate, canals, lines. What do you know? You know 12 feet. Oh, you know a depth. So you know this is 5. So H equals 5. So I guess this is 40 degrees. This is 40 degrees. So I guess W 40 equals H, which is equal to 5, and you also need this for the wetted perimeter, right? So you need this length here. So L cosine 40 is equal to W, I guess L sine 40 is equal to L. I guess you know L rather than W. And so those are the lengths you need. So the area, it's done here. The area is going to be 12 feet by 5 feet, which is this segment here. This by this by this. And this is going to be 5 feet, height times half base. Half base is going to be the width divided by 2. The width divided by 2 is just this this rearranged. This is the width divided by 2. There's 2 of them, so it's half width times the height, but there's 2 of them because there's one at this end and this end, so put them together, they just end up being a rectangle. So this is the area of the other part. Add them together, you get this. The wedded perimeter, they do it, is equal to 12 feet plus what we've called L. So this is H, this is H, right? Not L. And so this is this. It's 5 over sine 40, and there's 2 of them, one at this side and one at this side. So you have the perimeter. The hydraulic radius is just the area divided by the perimeter, which is whatever it is. This is the slope. And if you put them together in the recipe, the constant for English units, a Manning's coefficient, must be the area in square feet, the hydraulic radius to the power 2 over 3, and the Manning coefficient for whatever the channel is. That's it. So it's just a recipe. So nothing more than that. So, and you get out of that, you just have to be careful that you're using feet and seconds, and you get the volumetric flow rate, which would be in, I guess, feet cubed per second, cubic feet per second. Right? Okay. So that's it. So that's the for uniform flows. So for gradually varying flows, which are when this is no longer the case, we need to talk about a couple of things. We talk about wave speeds. Perhaps we won't talk about that in great detail, and we can define things in terms of specific energy. I thought uniform flows are where upstream and downstream depths are the same. Gradually varying flows are where it goes from some depth upstream to some different depth downstream. And that means that instead of being this, where the upstream depth and the downstream depth are the same, and the hydraulic grade line is also parallel to the bed, the slope S0 and the slope of the water and the slope of the energy line can all be different to each other. And so we need to be able to deal with that. So rather than going through, perhaps I'll see if I can derive it cold. Let's do it in this. So for gradually varying flows, the geometry you have is something like this. Where this is a length, we're going to have a channel with a flow in it, and that channel is going to have something like this. Getting lots of lines, and this is the horizontal. And so what we could define, if we a downstream and an upstream. This should actually be tapered to there. And let's put some components on this. This is the bed. This is Bernoulli 0.1. And this is Bernoulli 0.2. This would be our datum. I guess this would be Z1. This would be Z2. I didn't draw it very well, but then this would be delta Z. This would be the length between upstream and downstream. This would be our free surface. This would be, if it's perpendicular to the bed, this would be Y, but it doesn't really matter whether we draw it vertically or perpendicular to the bed that's sloping, because the bed's sloping so shallowly. Let's draw it slightly askew. So this would be y1 and this would be y2. And this by definition would be v1 squared over 2g. And this would be v2 squared over 2g. And this other portion here would be, it's called HL. All things we've seen before. And so the reason for writing it this way, so this would be our solid bed that it's flowing on. This is the water surface. This would be what we've called before our hydraulic grade line and our energy grade line. So that's our geometry. We're not necessarily requiring the y2 and are the same. y1 and y2 are the same. And therefore, if that's the case, then v1 and v2 aren't necessarily the same either. And so we could write out our energy equation. And that is going to be Z1 plus P1 over gamma plus V1 squared over 2G. Let's put this in for fun, just because we don't need it, just to draw the analogy, plus Z2 plus P2 over gamma plus V2 squared over 2G plus HL. So nothing you haven't seen before. This looked kind of strange because we don't have a pump in here. But we said before that what's driving, so this is zero. But what's driving flow, we said, is gravity. That's going from high potential here to low potential. So what we could also notice is that P1 is equal to Y1 gamma. And so also from that, I suppose, P1 over gamma is equal to Y1, just by rearranging this, which is useful because we have this here. We could substitute that here. So we could rearrange this as, so this is going to be Y1. This is going to be Y2. It's just saying that the pressure that acts at this point here is just the height of water above it. It doesn't matter that it's moving. It's just like a static swimming pool. And we could take these two off to the other side. So let's write this as Y1 plus V1 squared over 2G is equal to Z2 minus Z1 plus HL. We defined before that the head loss, the slope here, SF I think it was, SF is equal to head loss divided by the length over which it occurs. And also S0, which is the slope of the bottom bed, was equal to delta Z over L. And so what we could do is we could write these as that. Oh, sorry, I missed a term out. Why don't I do this? Hope you can do this. Might want to choose these other components here. And so what we could do is we could take these terms now, and if we want to, we could write this the other way round as y2 plus v2 squared over 2g plus hl over l times L plus, no, minus Z1 minus Z2 over L times L. Just done the same thing. Multiplied top and bottom by L. Y1 plus, believe me, this is much easier than the 10 pages of derivation that are written in the notes. And so we know that these terms here, this is what we've called SF, the slope of the free surface. So it goes from this to this drop as it goes downstream. That slope is just SF. And I suppose this is also equal to S0. So finally, we're going to call this, we call this term energy upstream is equal to the specific energy downstream plus times L. That's it. And so that's our energy equation. And so the one last thing we'd like to do is that if we look at our section as we go across, this is our cross-sectional area of flow as we go downstream. We know that if we have water across here, and the depth of this is y, as we've just said, and the width of this is b, uppercase b or lowercase b, and we have water going down at some velocity v average, then we can write that volumetric flow rate is equal to velocity times area, which is equal to average velocity times b times y. But what we might want to do is divide this up so that we have a section here which is flowing at some flow rate which we'll call lowercase q. So q is equal to volumetric flow rate over b, right? This is just a unit width. This is one meter, if you like. And so if that's the case, so we know that we have a width of a channel. We know that its depth can change because it can choose its depth to be shallow and fast or deep and slow. And so this might want this to be a variable. So if we include this down here, then this is average velocity times b times y divided by b. These cancel out, and we have that q is equal to v times y. And so alternatively, make sure that's true, we could write this as velocity is equal to q over y. And so the use of that is that we could substitute this into here. So if we write that expression out in long form, it's going to be y1 plus q squared over 2g y squared. It'll be y1 because it's at 0.1. And this is equal to the same for the lower energy. It's going to be q squared over 2g y2 squared plus SF minus S0 times the length over which it occurs. So it looks kind of complicated and stupid, but we're going to call this term here, again, specific energy upstream, specific energy downstream. And we're going to use that to say something about how we define flow rates in the system. So the interesting thing is that we define these. So this is the head loss that's in the system, which is the slope of the channel. This is the slope of the base of the channel. If we wanted to make life easy for ourselves, then we could merely put so for flat channel, SO equals 0. If there's no, I guess, if there's no slope of the surface, then SF equals 0 here. So these depths would be the same from upstream to downstream. Kind of negates everything we've done, but let's assume that that's the case. So either if both of these are 0, or if the components of these are 0. So in other words, if the slope of the base is this, and the flow above it is parallel to that, then these would also be 0. And this term would drop out. And we'd just be left with E upstream is equal to E downstream plus 0. Either if these are individually flat, or if they're individually the same slope because they cancel out. It's basically saying that the dissipation of energy in the system is exactly the same as the rate which gravity is driving flow. This is gravity driving flow, so this is the same as our delta Z term, or proportional to, and this is same as our head loss term, just to remember. And so our utility for doing this is that in this equation, Q, whether it's flowing upstream at a deep depth or flowing downstream at a shallow depth, is always the same. Continuity requires the same volumetric flow rate, has to be going through a unit width of the channel, unless the channel's slimming. And so what we can do is we can use that to maybe understand what's going on. So we've gone through this, we haven't done this. We'll come back to that. So this is what we did. So what we can do is we can look at how energy changes as we go downstream. So this is what we've defined already as our energy. It's the depth of flow, the volumetric flow rate per unit width, and the depth of flow, either upstream or downstream. If you take this expression and you multiply both sides by y squared, so if you multiply this by y squared, y squared, y squared, and substitute, take it off, you end up with the cubic equation, which defines that you have 3 potential roots. So what you could do is, in plotting the value of the energy that's upstream to the energy to the depth of flow, is that you could choose a value of volumetric flow per unit width, Q. So if you choose, why don't I draw it? So we have E is equal to y plus Q squared. Is it 2G y squared? Yes. So choose Q equals, 5 meters. It'll be meters squared per second, right? So 5 cubic meters per second width, but it's only 1 meter, so it'd be meters squared per second. And then cycle for y equals 0 to infinity. And if you do that, from what we just saw drawn, if we have a diagram that plots E versus depth, we end up with a diagram that looks like this. The diagonal, which is 1 to 1, which is y equals E, and you'd end up calculating for y equals 0, you'd end up with a number here. Y equals 0 would give you, actually would give you infinity, I think, but a small number would give you this. You'd end up with a plot that looked like this, like a nose. Never, always tapering downwards, still tapering. So it's parallel to this line here. Yeah, that's good enough. And it also has a component for negative. So if you take a specific value of energy, E equals something, then you have three roots. You're solving a quadratic equation. One's a negative depth, which makes no sense, but two are positive depths. And this red line ultimately asymptotes to this y equals E line, because if you take y as a big number, y squared in the denominator makes this term go to 0, and so you just have E equals y. So in the limit, as you do that, you'd expect it to do this. And so the physical interpretation of what this is doing is that it's saying that for a given energy state in your stream being driven as flowing, it could be flowing at deep depth but very slowly, or at shallow depth very quickly. And so physically what this looks like would be flowing along a flat channel. I want that to be blue. There we go. And it could be flowing either quickly or slowly. And the reason it might be doing that is because of this, because you have a sluice. Right? And so this is a gate that you put in the middle of the flow. This doesn't exist. So if I redraw, well, I'm going to leave that. So this is the water that's upstream. This is the water that's downstream. So this is Q. This is also Q. But since velocity equals Q over Y, this is Y here. So this velocity would be small, and this velocity would be large. This would be V2, this would be V1, right, in our system, upstream to downstream. So that's all it means. So to recap, all we've done is we've taken the Bernoulli equation with the energy terms in it, which are head loss and flow driven by gravity. We rearranged it to get the gravity term that's driving flow on the right-hand side, and it's given by the slope of the bed of the flow, which is this. The losses are given by the gradient of the free surface, and we can define that. And we can define it by these two energy terms, upstream and downstream. If energy is constant upstream, by making these loss terms and the driving flow term 0, which we could rationalize either by making them both 0 or making them equal to each other, then we have E1 equals E2. And E1 equals E2 is basically this. This is a constant value of energy. We've plotted for Q equals 5 meters a second, meters squared per second, a single curve. If we plotted a value for, can't remember, Q equals Can't remember if it's bigger or smaller. A different value inside there. It would look differently. But physically what that means is that if you can make the flow be deep, then it has to go at relatively small velocity. Or if you can make the flow be shallow, it has to go at relatively fast velocity. And it can take either of these two states because both of them are admissible in getting that. And so that's really what the curve represents. And so that's it. That's for gradually varying flows, I guess, is that you could have two possible flows because the free surface is a wild card, if you like, and it can be in either of those two configurations. So I'm not sure what else we have here. I won't talk about that. So this is it. Yeah, so Q1, so this is larger. So Q is larger here, and Q is smaller here, different flow rates as we drew it. So this is the same derivation. It's all written there. It's not particularly, I guess the other things that might be worthwhile doing is that these points on our curve are actually conditioned by our Froude number. And so this very tip of the nose, the minimum energy, so this would be the minimum energy here. And I don't know, I'm kind of running out of colors. This would be for a Froude number of 1, which is equal to the flow velocity divided by gravity times the depth, square root. Definition of Froude number is equal to the velocity of flow divided by the velocity of the celerity wave, right? Remember when we talked about waves, the tsunami wave velocity was equal to square root of g times depth in the ocean. It turned out to be something like 100 meters a second for Japan when we talked about that. And so this is the velocity that it communicates in information traveling upstream. And so when they're exactly equal to that, it happens to be at the minimum energy. If you look at everywhere relative to this, everywhere on this curve above this Froude number is greater than 1. And everywhere below this, the Froude number is less than 1. And this is what we refer to as subcritical. I think that's the, and this is supercritical. And I think I did that wrong, because these should be changed to the opposite. Greater than 1. So if you calculate the Froude numbers here, they're always less than 1. It's subcritical. It's kind of a lazy flow that's going at slow velocity. And if you're looking at the numbers below this, then they're always less than 1. In terms it's traveling faster than the value of the wave speed, which would carry information upstream. And so that, again, comes back to this figure, which we've suggested here. And what it means, this figure here, is that this is the flow velocity at the critical velocity, happens to be called at critical depth yc, and if the Froude number is less than 1, then it's subcritical. It means it's deep and slow. If it's greater than 1, then it's shallow and fast, and they represent those two parts on the curve. So this is your So this is sub, and the Froude number is less than 1, Fr greater than 1, and super. And this is energy, and this is depth. So that's an explanation of it. The other explanation of it, blah, 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 blah. The other explanation of the Froude numbers, or Froude numbers, are given by, if you think about the rate at which a wave travels. And so the velocity is equal to the length traveled over time. And so if you look at the length traveled, length is equal to velocity times time. So if you imagine dropping a pebble in the water, then the wave train would look like this as it goes radially outwards. But if instead of dropping a pebble, you think about tapping the water surface every second and looking at the waves which would come out for tapping it, then if you're tapping it the same spot in a stagnant, in a bucket, then they'd all be concentric, right? And the length that it's traveled would be equal to the velocity times time, which is up here. The velocity is going to be the velocity of the celerity wave, so it depends on the depth and what planet you're on. And if you're not moving, it will always look like this concentric rings. If you're tapping in the same place and the water's moving past you, then if you looked at the one that you did 10 seconds ago, and 9 seconds ago, and 8 seconds ago, and 7 seconds ago, no longer would they be concentric, but they would be skewed to the upstream. If you think about this, when the wave speed is exactly the same as the velocity of the flow, then the rings would look like this. It's like a plane going through at the speed of sound, the Mach cone, right? So the Mach cone is because all these... The plane was here at this time. The energy is trying to get away from the tip. It's going at the speed of sound. It gets this far away in the time that it takes for the tip of the plane to go to this point. From this point, the sound wave travels this far, and then the plane has to get to this point. So the Mach cone is just the locus of all the points where all the energy that's been traveling away from the tip of the plane has got as it moves downstream. The Froude number is kind of the same as that, except you're static and the water's going past you. So this is what the ripples would look like at a Froude number equal to 1. And so what it means is that if you're drowning downstream, and the only way you have to communicate upstream, if you're drowning here, and the only way you have to communicate is by slapping the water, and you're supercritical, then that information will never arrive if your savior is sitting at the water looking for a wave to come, because it can't go up against the current. If you're here, you'd be just fine. They'd be able to see it, but you can't. And so what it means is there's no information is able to get upstream if the flow is faster than wave speed. So if it's subcritical, then information can go upstream. This would be in the tall part above the weir, and information can come. If you're present downstream of that, then you'd make 10 seconds ago, you'd make this ring, and it would be carried downstream. 8 seconds, 7 seconds, right there. And it's all related to the... So it seems esoteric that we're talking about wave speeds. Why would we care? They're important for these open channel flows because they essentially tell you if you're able to send information upstream or not, which is how it knows how to organize itself in a flow. And so I think the only parts you need to know are the bits we've talked about. One more point, I guess... if you take this flow that we talked about, we know that this point here is a Froude number equal 1, critical flow. Critical flow occurs at a critical depth, which is YC, and at the minimum energy in the system. if we wanted to determine what the coordinates of that point are, we could be clever and we could just look for the minimum, where this minimum occurs. Easiest way to do it is, instead of having this plot here, is you just flip it the other way. So if you flip it so E is going upwards and Y is horizontally, then you look for the minimum energy in the system. We know that the minimum energy is where dE dy is equal to 0, by definition, right? This gradient at this point here is flat, so dEy is 0. If you take the derivative of this energy expression, derivative of y with respect to y is equal to 1. Derivative of y to the minus 2 is y to the minus 3, and there's an extra 2 that gets rid of this 2. And it turns out that the coordinates of this point are given by we can work out that the minimum energy occurs at a depth, critical depth, which is 3/2. So all it's saying is that the coordinates of this point are E min and critical depth to the 3/2, right? Yeah, 3/2. So if you know what the minimum energy is, you can immediately calculate what that depth would be if you wanted to know that. Or likewise, if you knew what that critical depth was, you could calculate what the energy was. That's it. So I think there's an example in here that does exactly what we're talking about. I guess this is the same example that we just did. So you could imagine having a weir like this. You can calculate for a given value, if you assume the base of this thing is flat, which it is. If you assume that we're not losing any energy in the system, then this whole term on the right-hand side goes to 0. You're just left with these terms. Continuity requires that Q1 and Q2 are the same. That's why we did that. It's the same as uppercase Q1 is also equal to lowercase q1. It's just that we've defined it now in terms of a flow multiplied by height, because that's useful to us, because we want to get that out of here. And if we know that the energy upstream and downstream are the same, then if we go through and make any of these curves, just by choosing a value of q and calculating for a range of y's what the energy would be, we end up with these curves. Don't care about the stuff below here. And then we can use that, if we know what the energy is at a particular location, then we can use that to be able to, I guess in this case it's this case. If we know the energy in a particular location, then we know that the upstream depth here is this depth. Which is this depth here. And we know that the downstream depth is this. And we can do some other gains. We could have a different flow rate, change the flow rates. This would be a lower flow rate, and this would be a higher flow rate in here. And depending on those, we could calculate what the magnitudes of the depths would be. That's it. So I think that's all. Yeah. So, and we can do all kinds of fancy things. So maybe we'll recap on that next time, but that's the essence of gradually varying flows, I guess, and what we need. So you just need to define things in terms of an energy equation. It ends up being no different than the energy equation, which is Bernoulli equation with HL, H sub L, and driven by gravity, and we can define it in terms of those terms. So, okay. A useful thing for 9 days from now. Straightforward test. Okay. So next time, I'm not sure we have a very long session. We'll talk about rapidly varying flows, which are hydraulic jumps, which are probably more involved in this for this class than we need. But anyway, we'll talk about it and close things out on Friday. Great. Thank you. Have a great day. Safe travels for those traveling.